But let's start by doing the Laplace transform example. And I'll go ahead and pick one that's different than the one that in the video that I made yesterday. And that does have a discontinuous forcing function. So I'm looking in section 6.3. And why don't we think about doing, say, problem number 30. If you got your book, it's on page 600. So the second derivative with respect to t twice plus 6 times the first derivative plus 13 times the function equals 13 u4t. What is u4t? I'll say that in a second. The initial conditions are y of 0 equals 3 and y prime of 0 equals 1. So mass on a spring, normalized so we could pretend the mass itself is 1. The mass could be thought of as the coefficient of the acceleration. Spring constants, 13 newtons per meter would be the units of that. 6, that would be the damping coefficient. It's in front of the velocity. It would be in like newtons per meter per second. But what is this? This is a forcing function. And what is u4 of t? u4 of t, it's called a unit step function, also called Heaviside function in honor of somebody whose last name was Heaviside. That equals 1 if t is greater than or equal to 4, and 0 if t is less than 4. So 13 times it equals 13 if t is greater than or equal to 4, and 0 if t is less than 4. So essentially, this is a homogeneous equation at time 0. There's no external forcing, but after 4 units of time, all of a sudden there's this external forcing that sort of switches on at one instant in time to be constant at 13 times 1 at that instant in time. What kind of physical situation could that happen? Maybe a mass on a spring that's on a table, and all of a sudden at time 4, maybe the table breaks to some degree and like flips to its side to a certain degree so that now gravity comes into play as well. So gravity is essentially the constant external force, 13 times 1. That's one kind of situation where possibly something like this might be a good model. You might wonder whether it would introduce somehow discontinuities in the position or velocity or the acceleration of the mass. And the answer is it can, at least in the model. And in real life, the discontinuity, probably in the velocity and acceleration, does affect the motion. It is related to the motion, and something you could probably still observe in the motion, like the velocity just changing so rapidly that it's easiest to model it with a discontinuous function. All right, so as usual, we take the Laplace transform of both sides of the equation. Use linearity. I'm going to do 2 steps at once, essentially, here. The Laplace transform of this linear combination of a second derivative, of a first derivative, and the function itself. Because the Laplace transform is a linear transformation, its operation preserving would be the Laplace transform of the second derivative, which I'll just write with primes here to save room, plus 6 times the Laplace transform of the first derivative, plus 13 times the Laplace transform of the function y itself, equals the Laplace transform on the right-hand side, which can be thought of as 13 times the Laplace transform of u4 of t. Big picture. Where are we going big picture with this? We're trying to solve the differential equation. We're trying to find little y as a function of t. You take the Laplace transform, you use its properties, and that typically or often allows you to solve algebraically with no calculus for the Laplace transform of the unknown function y. And then, in a sense, it's like you're finding an antiderivative almost, though it's definitely not the same thing. you take the inverse Laplace transform of both sides to find the function. But the details can get very complicated. Besides linearity, one property you need is how the Laplace transform affects derivatives. And this has the benefit of also bringing the initial conditions into place. So when we take the Laplace transform of both sides, the initial conditions are used almost right away instead of at the end. So one property is that this is S times the Laplace transform of y, S being the variable for a Laplace transform of a function of t. It's just traditional to use S, minus y of 0, but y of 0 is 3. So for this problem, this becomes S L of y minus 3. And we're also going to multiply it by 6 because it's 6 here in the end. This thing is related in a very similar way to y prime, because y double prime is the derivative of y prime. You could write this as S L of y prime minus y prime of 0. Y prime is playing the role of y. And then you can use the same property again on this part. That's S L of y minus y0, and therefore, when you put those facts together, this entire expression becomes, you got to multiply S through here, S squared L of y minus S times y of 0, then minus y prime of 0. Since y of 0 is 3 and y prime of 0 is 1, this becomes S squared L of y of 0 is 3, so we get minus 3s, y prime of 0 is 1, so we get minus 1. Is that big enough? See? Oh, bring the phone down a little bit. Okay, this is different than the example I did in the video I made yesterday. One thing about the video example I made yesterday with a second order equation, I do 2 Laplace transform examples. One difference is that the initial conditions are both 0. The other difference is in the video problem, the right-hand side function actually is a trig function. I think it was cosine of 2t or cosine of 3t, which could also be solved by complexification, chapter 4. And without the help, the complexification approach is actually easier than the Laplace transform approach. But here we have a discontinuous forcing function, so it's definitely better to use the Laplace transform, even though it's not super easy or pleasant. Kind of fun when you don't make mistakes, but it's just very, very easy to make mistakes. So now once I've used those facts, this one, well, those two, don't forget about to multiply this one by 6 and this thing by 13. The left-hand side can be you can isolate L of y is what I'm trying to say. It's an algebra equation you can solve for L of y. You would want to, well, don't forget about multiplying by 6 here. You would want to add 18 to both sides, 6 times 3. You'd also want to add 3s and 1 to both sides. They cancel the minus 3s minus 1 there. So in the end, you're adding 3s plus 19 to both sides. On the left side, you would still have a Laplace transform times s squared and times 6s and times 13. So you could factor it out, and you could write s squared plus 6s plus 13 times the Laplace transform of y equals 13 times the Laplace transform of u4t plus 3s plus 19. Which I can now divide both sides by this to isolate L of y. But there's still the question of what L of u4 of t is. I won't take the time to derive it, but the book does derive the Laplace transform of a general unit step function with discontinuity at t equals a. And you should have even read about it already. It's on page 579. It's right there. UA really of t equals e to the negative as divided by s. There we go. A in our problem is 5. So I get e to the 4, excuse me, e to the negative 4s divided by s. This thing here is e to the negative 4s divided by s. And the fact that there's an e to the negative 4s in here is another part of what makes the problem harder. Because when we solve for L of y, it's not going to be so clear what the inverse Laplace transform is going to be for part of this. But I could say L of y, which I should also mention, by the way, some people call capital Y of s. I typically stick with the L, is, don't forget to divide by s squared plus 6s plus 13. So here we get, just leave the 13 out in the front, 13 times, I'm going to bring the e to the negative 4s out in the front as well, e to the negative 4s times 1 over s times s squared plus 6s plus 13. And then don't forget about this term over here, plus 3s plus 19 over what I divided by s squared plus 6s plus 13. And this means the solution function, little y of t, is going to be the inverse Laplace transform. Well, 13 times the inverse Laplace transform of e to the negative 4s times 1 over s times s squared plus 6s plus 13 plus the inverse Laplace transform of this fraction, 3s plus 19 over s squared plus 6s plus 13. So whatever those inverse Laplace transforms are, once we found them, we found the answer. But it's not so easy. How do you do this? Well, let's focus on this one first, without the e in there.
Did we have to split them up? Like, would you recommend always splitting them up?
Yeah, you want to. You want to have two terms here that are added. We need some more information about how to solve these here. One thing to keep in mind is, since it is a forced damped harmonic oscillator, probably the answer is still going to involve exponential decays and trig functions. So somehow, in all this mess, exponential decays and trig functions are going to come into play, because it's a damped harmonic oscillator. Another thing that, if you think about it intuitively, must have to come into play is, since the forcing function is this unit step function, where something changes from 0 to 13 at t equals 4, when t is between 0 and 4, the answer must be simpler, corresponding to 0 on the right-hand side, a homogeneous first order equation or second order equation that we could have solved way back in chapter 2 with guessing YH, with thinking about eigenvalues essentially like s squared or lambda squared plus 6 lambda plus 13 equals 0. 6 squared minus 4 times 13 is negative. The eigenvalues would be complex numbers. And that's, we've got enough damping here that we still have oscillation, or we have little enough damping that we still have oscillation in the solutions. Yeah, trig functions for sure are going to become involved. And somehow the answer's got to change in some sort of kind of discontinuous way, maybe at time 4. How do you account for such a change in a formula? With this function itself, u4 will probably come into play still. Give you an intuitive idea what to expect. But yeah, let's deal with the simpler one first. What do you do? Well, it's tricky. You might think, okay, do I use partial fractions? Do I factor this bottom and use partial fractions somehow? That would be nice if you could. Problem is, s squared plus 6s plus 13 has complex roots. It's an irreducible quadratic over the real numbers. You can't factor it with real factors. So what do you do? It's a trick. And here's the trick. Now I'm just focused on that denominator here. S squared plus 6s plus 13. Though you can't factor it, you can complete the square to rewrite it in what's called vertex form. This is pre-calculus. Take the coefficient of s, 6, divided by 2 to get 3. 3 squared is 9. Rewrite this function as s squared plus 6s plus 9 plus 13 minus 9 to cancel the 9s, which means 13 minus 9 is plus 4. And the reason I did that is because this part right here is now a perfect square. It's s plus 3 quantity squared plus 4. And 4 is also a square. I'm going to write it as 2 squared. And the reason this is helpful is twofold. One reason it's helpful is because it's going to help relate to cosines and sines. In section 6.3, they derive, first of all, the Laplace transform of sine of omega t. Actually, they derive it not by doing this integral, but by solving this initial value problem whose unique solution is sine of omega t. And they find ultimately that the Laplace transform of sine of omega t is omega over s squared plus omega squared. And they also find the Laplace transform of cosine of omega t to be s over s squared plus omega squared. Pretty similar answers. And why are these helpful? They're helpful because look at the bottom of them. S squared plus omega squared in both. This is almost like that. It's s plus 3 squared plus omega squared, where omega is 2. But it's close to being s squared plus omega squared. And it is in the bottom of this. That's part of the key to solving this. Another part of it is yet another property. In section 6.2, there's the shifting on the t-axis property. And in section 6.3, there's a shifting on the s-axis property that says the Laplace transform of a function like that, e to the at times little f of t, is capital F of s minus a, where capital F of s is the Laplace transform of little f. How's this helpful? These properties are usually helpful in the other direction. The inverse Laplace transform of a function like this is a function like what you see inside there. S minus A, S minus A. How is S minus A relevant? Well, S plus 3 is S minus negative 3. A is negative 3. I guess. It's still in the bottom there, so you wonder what do we do about the numerator? Well, this is always super tricky. Can I get it right? What I also want to do here to help me finish this is think of that fraction 3s plus 19 over s squared plus 6s plus 13. I've already rethought of the bottom as being s plus 3 quantity squared plus 2 squared. Let me replace in the numerator s with s plus 3. But wait a minute, how can I do that willy-nilly? replacing s with s plus 3 is okay, as long as I also subtract off 3 times 3 to make them equal. And then I can break this apart into 2 fractions, one of whose numerators will involve s plus 3, and one of whose will involve a constant. I could rewrite this as 3 times the fraction s plus 3 over s plus 3 squared plus 2 squared plus 10 over s plus 3 squared plus 2 squared. But I'm going to think of the 10 not as 10, but as 5 times 2, so that the 2 there matches the 2 there. Because the 2 is going to be the omega from the Laplace transform of sine omega t and cos omega t. And the a from the shifting on the s-axis property is going to be -3, because s plus 3 equals s minus -3. All this means, okay, let's write it out, that the inverse Laplace transform of this thing is 3 times the inverse Laplace transform of this thing plus 5 times the inverse Laplace transform of this thing. And the inverse Laplace transform of these 2 things, by the properties I showed you in the book, are going to involve cosine of 2t and sine of 2t, omega is 2. And they will also involve the shifting on the s-axis property with a equal to -3. Let's look at again at that shifting on the s-axis property. Right here. Think about this for the inverse. The capital F, let's focus on the second one here. That's the thing I've circled in red there that I'm pointing at is the capital F of s minus a, where a is -3, because it's an s plus 3 there. Where capital F is the Laplace transform of either sine of 2t or cosine of 2t. Which one? When the omega is up top instead of the s, that's the sine one. Omega up there, not s. So this thing is going to involve a sine of 2t, but what else does it involve? It involves e to the at, where a is -3, e to the -3t. This thing here is e to the -3t sine of 2t. That's what that inverse Laplace transform is. Oh, wait a minute. Oh, no, sorry. No, that is right. Oh, I've got myself confused. Double confusion leads to the right answer. Okay, that is right. I was thinking for a moment there it was wrong, because I was thinking that what we did had to involve the shifting on the t-axis property, but it doesn't yet. Okay. We're focused on this one that doesn't involve the e there. This one is going to involve cosine of 2t, and still an e to the -3t in front. This one is e to the -3t cos 2t. Because Laplace transform, well, this is taking a lot longer than I hoped for, but I think it's still worth it. Laplace transform of cos 2t was this, when omega is 2 squared there. And we're once again using this property with a equal to -3, and we get e to the -3t in front of the cos 2t. That's what this is. This begs a question then. What do you deal with this? How do you deal with this? It's even harder still. And I think I don't have the time to finish it really. You would want to use partial fractions here to rewrite that fraction 1 over s times s squared plus 6s plus 13 as something over s plus some constant over s plus, since the bottom is an irreducible quadratic, you need a linear function up top, b times s plus c. And you'd have to solve for a, b, and c. Once you found a, b, and c, you could do something similar to what we did here. Do the completing the square thing in the bottom. Do some creative algebra to rewrite this part. I'm focused on that part right there, not this part, as something times something similar to this plus something times something similar to this. And this part would be simpler. You don't have to worry too much about that part. But the final step would be the hardest step of all, because we have to take the inverse Laplace transform in a similar way that we did down here. We'd have to use the shifting on the s-axis property. We'd have to use this property again still, and we would get exponential decays in, as well as trig functions, cosines and sines of 2t still. And I think the a would still be -3, so we'd still get e to the -3t cos 2t and e to the -3 sine t 2t with more complicated coefficients in all likelihood. But we wouldn't be done, because we'd also have to use the shifting on the t-axis property, because the u function is in there. This one. The e to the -as is in there on the inside the inverse Laplace transform. So our answer is going to involve UAT, where in that case, A is 4. And that's how U4 of T would become involved. Don't have the time to do it. You can see it's a really, really big pain, but it does solve the problem. It does get you to the solution when you fix any mistakes you make. Now, again, the sample problem I made yesterday in the video, the right-hand side was a trig function. There were still similar calculations that need to be done, but I told them people when I gave that exam problem what the results were, and they just had to finish it, which makes it a doable problem in even 5 to 10 minutes. Okay, instead of this one where if I'm going to finish this, it's probably going to take me another 10 minutes, and I very easily could make a mistake. It's worth practicing these, at least 1 or 2 of these in section 6.3 though. I think to really see how everything fits together for the sake of understanding. I think it's worth practicing. Even though I give you some steps on the test, if I gave you a problem like this, to help make your life easier and my life easier. And focus on the key things and not worrying if you make a small mistake. If you make a small mistake and don't get the answer I say it's going to be, then you just go from there. We don't go past 6.3 through lecture 36. I did make a lecture 37 that's not required to watch, which continues talking about Laplace transforms and a kind of forcing the function that's related to something called impulse forcing, a delta function, which is related to hitting things with hammers, for example. But I did say the very last couple sections, especially if you're an engineering major, are worth eventually studying. Convolutions, which is a hard topic in itself, and qualitative theory of Laplace transform in the last section. Those I know, even though I'm not an engineer, I know from reading other engineers talking about it, that that's the most important stuff for electrical engineering. One electrical engineer that I'm thinking of when I say that, somebody that Barrett is related to, who died about 10, 15 years ago. I'm forgetting his name. R.A. Carlson, yeah. I should not forget his name. Very famous physics professor at Bethel, who died about 10, 15 years ago. And He was always thinking about this stuff, okay? He was an electrical engineer, I think by trade or something, but he maybe mechanical. But he taught here for a while in physics. He essentially started the physics department in the 70s. And yeah, he liked Laplace transforms too, like Karen Rogers does too. All right, what should we do with the remaining time? What did I say I was going to do? I forgot. I did say it. Oh yeah, look at the PowerPoints for the last couple lectures and kind of highlight some things to know about other things that are plenty complicated in their own right and are not enough of a focus to put long exam problems related to them on your exam, but maybe shorter true false multiple choice, maybe short answer, maybe. I did make in the video yesterday, I did do a proof related to the concept of an unstable equilibrium point. I will not put a proof on your exam. When I taught this content as a plain differential equations course, I did work through this proof also in class, and I did have them do that on their old exam. And I put it on the video yesterday, but that's one you can skip. It's the second problem in the video. The first problem is a shorter Laplace transform problem. The second problem is about proving something's unstable. Should you know the basic idea of unstable? Even the basic idea is perhaps too complicated, except to know the things that I said about how this stuff is related to typical kinds of examples in the plane, say. And that does come up in a true-false question that I did yesterday. Stability has got this technical definition that you were just looking at that's related to whether or not an equilibrium point is observable. Think of a pendulum, okay? With friction, say, swinging back and forth, not a mass going back and forth, but a pendulum swinging back and forth with some friction. There is an equilibrium point that is physically observable, the straight down position, right? Even if you give it a kick, it's gonna, because of friction, approach the straight down position. That equilibrium is observable. It is stable. A small perturbation, a small kick to the graph, or to the pendulum, results in motion, but the motion stabilizes toward equilibrium in an oscillatory way. You get like a spiral sink in a phase point. Sinks and spiral sinks are stable. In fact, they're also what we call asymptotically stable, in that the solutions also approach the equilibrium point as t goes to infinity. So stability means it's observable. Asymptotically stable means it also gets approached, which makes it even more observable, you might say. Centers, however, where you got periodic solutions going around an equilibrium point, those are stable, but not asymptotically so. Can you really observe a center? Well, kind of. You can observe small oscillations about a center. So this would come up in a mass on a spring or a pendulum if there were no friction. Somehow magically no friction. Then you would observe the center equilibrium point. And the fact, for one thing, if it was pointing straight down, it would move. Even if you give it a little kick, it doesn't approach the equilibrium with no friction, but in a sense, the equilibrium is still observable because we are seeing small oscillations about it. Unstable equilibrium points correspond to unobservable phenomena, like a pendulum pointing straight upward, whether there's friction or not. You're never going to observe that unless you cheat and glue it, right? Don't cheat. Don't make the friction infinity effectively. Because if the friction is not infinity, even a tiny little deviations from perfectly straight up is going to result in the pendulum swinging. And so you're not going to observe the straight up position if you don't cheat. That's unstable. They correspond to sources. Sources are unstable, whether spiral source or non-spiral source. And they also correspond to saddle points. Saddle points are also unstable. You're not going to observe a saddle point. In fact, the straight up position of the pendulum is a saddle point, not a source. There's technically in the math a solution, excuse me, physically speaking, that would be represented by a pendulum that has been sticking straight up since before creation. And here, as you're watching it, all of a sudden it goes like this, and then it heads towards straight up as t goes to infinity. It never reaches it. You're never going to observe that, right? It's technically there in the phase plane in the math. It's a separatrix solution. But that intuitively is why the straight up position is not a source, but instead is a saddle point. There is a separatrix solutions that go toward it in the phase plane. But it is still unstable. So these are unstable. These are stable. And this one's asymptotically stable. And I drew it as a spiral sink, but I could have drawn it also as a real sink. Asymptotically. Maybe I also should add a real sink in here. There are theorems that are kind of complicated. This one is, in essence, says if the equilibrium point is hyperbolic, which means none of the eigenvalues have zero real part. So none of the eigenvalues for the Jacobian matrix are zero, and also none of them are purely imaginary. Hyperbolic equilibrium points are important because that's where Hartman-Grobman applies, and you can say linearization gives you a good approximation to what's happening. Non-hyperbolic equilibrium points are where bifurcations occur. For a linear system, when you've got a zero eigenvalue, determinant of A is zero, there are infinitely many equilibrium points. They're all non-hyperbolic. Strange equilibrium points, you might say. There are stranger things that can happen as well, including a weird kind of saddle point in the video I made yesterday for a Hamiltonian system. But this is saying if all the eigenvalues have negative real part, they're either real numbers that are negative or complex numbers with negative real part, then it's going to be asymptotically stable. This theorem is about Lyapunov functions and how they can be used to detect whether an equilibrium point is stable or asymptotically stable. And it's based on the derivative of the Lyapunov function like we talked about with gradient systems, and whether it's always negative or not. I'm not going to ask you to state these things on the theorem, on the test. You should know the basic idea for true false multiple choice questions, like I've just verbally been describing for the past 5 to 10 minutes at that level. And I do talk about it intuitively in the lectures as well. Structural stability, I'm not going to test you on that, but it is an important concept in more advanced classes. Essentially saying that if your phase portrait is satisfies certain properties and you change your differential equations a tiny amount, the phase portrait's not going to change very much. That's what it means. No bifurcation is going to occur. Stuff about Laplace transforms. Then in the lecture C's, there's C's, I get into partial differential equations. On the video yesterday, the one question I had about partial differential equations was related to this heat equation here, and whether a certain function that was a relatively simple function solved it or not. And actually it did, solve it. The question was, what was K to make it a solution, is what I asked them last year about this. So I could ask you something similar. I could ask you true, false, here's a function, does it satisfy the heat equation or not for some K? The function would have to be fairly simple so that it wouldn't take too long. This is a partial differential equation and involves partial derivatives. U is a function of two variables, t and x, time and position along, say, a thin rod, a metal or something. You should be able to tell when a partial differential equation is a heat equation. Can I write it in one of these forms? We'll focus on the Leibniz notation form for the test. Can I write it like this if I maybe rearrange a little bit? But there's other partial differential equations I could write down that could not be written that way, and you should be able to say, no, that's not a heat equation, not a form of the heat equation. I think you should pay attention graphically to what happens to solutions of the heat equation as time goes by. They are typically representing temperature distributions. And if you imagine the x-axis as being an infinite rod, and there's no external heating being applied, essentially the temperature should approach zero as time gets larger and larger. So qualitatively, the graph is going from red to pink to orange to blue here as time goes by. The temperature is evening out. That's what happens in an infinite rod case. If it's a finite rod, other things can happen, especially if you keep the temperatures of the rod at the endpoints fixed, which you evidently can do. Or if you're injecting heat into the system. This one here, you can see the initial temperature distribution is the red graph. And again, it's being smoothed out. The heat is flowing from hot areas to cooler areas is the intuitive idea that you should know what that it represents. In lecture 36, the last lecture, I talk about higher dimensional systems, phase spaces that can be cylinders or spheres instead of just planes. You get pretty pictures. There can be systems that conserve quantities like Hamiltonian systems do, but actually in 3 dimensions, Hamiltonian systems don't exist. You have to do an even dimensional system for it to be a Hamiltonian function. It turns out I won't explain why. But you should be able to do a partial derivative calculation like this. If I asked you, that's something you should be able to do. I'd probably make it simpler if it did. It did come up in the video I made yesterday in a simpler example. Yeah, this is just, it's interesting stuff, but you don't need to know it. This is stuff that I just was in the last PowerPoint as well. This is an example with Lyapunov's second method. It's a one-dimensional example, which makes it easier, but I wouldn't have you do a problem like this. This one I did in the video yesterday related to polar coordinates and trapping regions and Poincare-Bendixson theorem that I had you read about. Probably I would not give you one where you have to do all the details of the calculations like I show in the video, but you should know that if you've got a trapping region in the plane and there's no equilibrium points inside, there's got to be a periodic solution inside. Talked about this on Wednesday. And typically your trapping regions in such situations are going to be an annulus shape, ring shape. And to be a trapping region, one sufficient condition is the vector field points into the region all along the boundary. So if you know that's the case and you know there's no equilibrium points inside there, there's got to be a periodic solution. You should know that. And the theorem that guarantees that is called the Poincare-Bendixson theorem. So true, false, multiple choice type question there. Where'd the PowerPoint go? Here I just bring in more examples with a linear system that has a Lyapunov function and a nonlinear system, actually. And the details here are pretty nasty. You wouldn't have anything this depth on the test. Hessian matrix here instead of a Jacobian matrix involves second order partials. You don't need to know about the Hessian matrix. More on Laplace transforms, and then the last part of lecture 36 gets into more in the weeds on the heat equation, actually trying to solve it. This will be what's most useful for you in math methods, but I'm not going to test you on the full details. It does involve a technique called separation of variables, but it's different than separating variables from chapter 1. And it's more complicated. And ultimately, infinite sums of analogous to Fourier polynomials, which are called Fourier series, help you solve the partial differential equation. And related to that is inner products on function spaces. You can write down the formulas for the Fourier coefficients without talking about inner products. But to realize deep down what you're really doing, it's best to relate it to inner products. And a big benefit of that realization is something you could encounter in engineering school. More general kind of signal processing, more general kind of image processing, where you go beyond using Fourier series and Fourier transforms, and you use things called, well, one thing is called a wavelet. If you've ever heard of wavelets before, it's related to all this stuff in more general settings. So perhaps, I mean, detailed, tricky calculations here, very easy to make mistakes. They'll come up in math methods. And to fully justify everything needs real analysis, which we definitely don't do. But realize in the back of your mind, and maybe for a true false multiple choice question, that all this stuff is still related to linear algebra. It's differential equations that's still related to linear algebra. The more general linear algebra, function spaces, which are vector spaces, on which you have an inner product defined by an integral of a product, which is analogous to dot products for vectors in Rn. And orthogonal projections are still relevant and still give you answers, and still can be, you can try to visualize it, but only by analogy. By the way, I should mention also that when you talk about a norm of a function defined by an inner product, the square root of the inner product of the function with itself. And if the inner product is defined by an integral, that's going to be the integral of the square of the function over whatever interval you're talking about. And by the way, if you change the integral, then you are changing the inner product and you are changing the norm. But this is still related to intuition. It's not pulled out of a hat for no reason. A function will have a small norm, a small magnitude, if its graph is relatively close to 0. It doesn't get very big. If this is the graph of f, then f, the norm, will be small. On the other hand, if the graph goes far away from the axis, then the norm of this function, oops, didn't pass the vertical line test there. The norm of that function will be large, because it'll be small because this integral will be small. And it'll be large over here because this integral will be large. So you can think about these things intuitively. It's not just completely pulled out of thin air, is what I'm trying to get across. There are good reasons to think of norms in this way and inner products in this way. and distances in this way. Distance between two functions f and g is the norm of their difference. Just like the magnitude of the difference of two ordinary vectors effectively measures the distance between them. There's the vector x minus y. If x's and y's heads are close together when you put their tails at the same spot, then x minus y is going to be a short vector. The distance between the heads of these vectors is small. To end the semester, let me just think about what we've done and talk about it for 5 minutes, and then we'll go a little early. I'm going to aim for 5 minutes. As you know, I often said this class could be called discrete and continuous dynamical systems. Differential equations is the continuous part. Linear algebra with difference equations is the discrete part. Dynamical systems mean systems that change over time. Dynamical. Sometimes called dynamic systems, because I think dynamical is not officially a word. But whatever. So you start with simple models, exponential growth, exponential decay, linear differential equations, linear difference equations. Along the way in chapter 1, we develop other techniques for thinking about them besides symbolic. I mean, separation of variables is symbolic. But then we also think about slope fields and graphing sequences and numerical techniques like Euler's method. And we want to have some theory like existence and uniqueness. Then later in chapter 1, besides dealing with vectors with linear algebra, we're also talking about interesting things that can happen when parameters change, bifurcations. Other techniques like integrating factors, method of undetermined coefficients. Then we move through the linear algebra more, we get into higher dimensions, matrices, vectors in higher dimensions, also in the differential equations. That's ultimately where the eigenvalues and eigenvectors comes into play, motivated by straight line solutions for differential equations. And for difference equations, they're sequences that lie on straight lines to the origin. And all that linear algebra can be related to change of coordinates with diagonalization, P matrices. And then since then, we've had, you might say, more specialized techniques with complexification, using complex numbers. For nonlinear systems, I mean, we talked about null lines along the whole way, but then there's also linearization and Jacobian matrices. And now finally, Laplace transforms and PDEs and higher dimensional problems. Okay. That's a real quick, I guess that was 3 minutes overview of the course, but the main thing is, change over time. And, the harmonic oscillator model is just sort of like the simplest thing to think about. That's still significant beyond population growth problems and stuff like that, I guess. And so that's what we emphasize for the most part. Do know if you go into electrical engineering that harmonic oscillators occur in electrical engineering as well, not mass on a spring with position and velocity and acceleration. You're thinking more about current and capacitance and whatever, voltage and that kind of stuff. But similar differential equations apply. And it also comes up in other classes, including quantum mechanics. Okay. And complex numbers don't go away either. They're a useful tool. Do you have anything else you're wondering about? Either procedure-wise or content-wise, something? No. Guess it's not snowing real heavy yet. It's not accumulating yet. So here on Tuesday, 8 a.m. I know it's a tough course with a lot of content, but you guys have worked hard. Finish well. It is important. As Paul says, run the race to win. Okay. All right. Have a good day.